So thanks everybody for joining the Boundary Layer Urban and Land Processes seminar. This is our first one of the spring term. We do have several, so please come back. We have a handful of folks online as well. Matt Ammon will be our first speaker, and Matt works with myself, Josh Gebauer, and a handful of other folks looking at WoFS and convective events and how we can use boundary layer observations in a network. And so it's pretty cool work. We're really excited about it, and I'm excited to see what Matt has to show us. So take it away.
All right. Thanks, Liz. I kind of had a start plan, but she just basically did it for me. So no, that's totally fine. But happy first BUL seminar of spring 2025. And also happy annual middle of the night Norman Tornado Day. So I'm excited to get started off the spring with talking about my master's research, which, as Liz kind of said, is focused on exploring how we could use boundary layer profiling systems in a network to improve how convective models forecast severe storms. So it's a wide range of things that can be focused on for this. So I'm just kind of giving a caveat now that I decided to kind of hone in on kind of a small part of the results and spend time going in depth into those results so that you guys can digest them and I'm not just spewing out a bunch of information. So the amount of content is a little bit low, but it's important to narrow it down with the nature of this type of topic. But this project primarily motivated by the atmospheric boundary layer data gap, which I'm sure a lot of us in here are very familiar with. And a lot of us in here are also very familiar with the fact that the atmospheric boundary layer is severely undersampled, right? We have observations above the surface only operationally only at radioson sites that are launched at 100 or so sites across the country that are spread hundreds of miles apart and 12 hours apart between launches. And there's a lot of stuff going on in the boundary layer that evolves really rapidly and really locally on scales that are much smaller in space and time than our current operational observations are able to pick up on. And these processes and features like boundaries, bores, coherent turbulence structures, they all can play a huge role in how convective storms develop and evolve. So being able to understand those features and how they're evolving and what they're doing to the atmosphere is ultimately an important part of improving how we forecast severe storms. So with that, if we have a network of boundary layer profilers that is continuously giving us observations of the boundary layer, we could hopefully theoretically pick up on some of the impacts of those features and processes. And if we assimilate those observations into convective models, perhaps we could therefore improve the forecast performance. So in order to kind of explore this idea, we are going to focus on it in the context of two specific cases, both of which are pretty relevant to us, both of which involve significant tornadoes in Oklahoma. Both of the cases also kind of had low predictability. They were hard to forecast. And so they made for interesting forecasts and made for good cases for this project to see how the forecast could have improved with a boundary layer profiling network. So the first case is February 26, 2023, the case of the QLCS Norman tornado. And this case was extremely highly forced. We had a very robust upper and mid-level trough with extremely powerful flow, a ripping low-level jet. The kinematic parameters were upper echelon essentially. But there was some uncertainty with this event regarding instability, especially as the QLCS moved eastward into the overnight hours when models indicated that, as we would expect, the boundary layer would become stable, nocturnal boundary layer. So there was a lot of kind of uncertainty regarding how that would influence the risk for tornadoes and severe weather in general as the QLCS moved east. But despite that, the most significant tornado of the event occurred at 10:30 p. or I guess it was 9:30 p.m. It's just before daylight savings, right here in Norman. And observational soundings showed an extremely strong capping inversion and very minimal instability. So it was kind of something that was a little bit unexpected and surprising. And here's my picture from that day, because this tornado hit the Ave apartment complex where I was living. And here is someone's washer and dryer just out in the grass alongside a plastering of insulation. So just kind of to show the relevance of this case. And in case 2, April 19th, 2023, this was an entirely different synoptic setup. It was very weakly forced. There was not, there you could see in the 500 millibar analysis there. There's maybe an embedded shortwave, but it's not a very very well-defined trough, and there's not very well-defined forcing. So with that, there's a lot of uncertainty as to whether or not convection would actually occur. In fact, most CAMs up until just before the start of the event didn't show any convection. They all showed that the cap would likely prevent any convection from occurring. And that was highlighted in the SPC's convective outlook. As you can see, this localized outbreak of tornadoes right around here occurred pretty much outside of even a 2% in terms of the morning convective outlook. Now, this was updated just before the start of the event when a special sounding showed that the cap was actually a lot weaker than expected. So this event, a boundary layer profiling network, could have been huge for improving how it was forecasted. We could have seen in real time with rapid updates the strength of the cap, how it was probably weaker than models indicated, and just how the atmosphere was evolving in real time 3-dimensionally in a way that could have improved not only for real-time forecasters, but potentially the forecast output of convective allowing models if they were assimilated into those. So with these events, obviously we did not have a network of profilers out there, as nice as it would have been. So we have to, before I go on, here's another picture that I took of a tornado from that day, just for fun. But in order to test what utility a network could have provided, we have to rely on simulations. So we have to rely on simulated observations. And we do this by using observing system simulation experiments, or OSSEs. So what OSSEs do, is they use what's called a nature run, which in this case, we identify the nature run to be the best performing member of a WoFS ensemble run, a WoFS 1 kilometer ensemble run. And best performing was pretty subjective. We pretty much looked at all the different ensemble members and figured out which one most accurately depicted how the convection in the environment evolved on this day. Nature run serves as kind of a proxy for the real atmosphere. Since it's kind of the most accurate ensemble member, we assume that it has conditions that are most close to what actually was observed. And of course, it's not going to be perfect. So that's a huge limitation of this. But we can use the nature run to simulate observations that could come from a boundary layer profiling network. And these were done using some pretty comprehensive observation simulators that take into account the errors associated with different profiling instruments and correlation errors and stuff like that. So with this nature run, or alongside this nature run, we have the control run, which is what the experiments are run from. And this is the worst performing member of a WoFS 3 kilometer ensemble. So the hope is that if we assimilate these simulated observations that we generated from the nature run into the run that was the worst, or the ensemble member that was worst performing, then we could see kind of, in theory, what improvements those observations could have made if they were assimilated. So that's kind of how we did this without actually having observations directly from the field. And these here are the domains for the two cases. So the orange is the nature run domain. So this is where we're assimilating the observations from. And within the nature run domain, you see all of the Oklahoma mesonet sites. Oops. Along with a few sites that we kind of made up to be in Texas, just to kind of have comprehensive coverage of the nature run domain. And this is the same thing, but for the other case. And then the blue is what we're assimilating observations into. So all the experiments are run on the blue domain. So the data assimilation of these observations, I'm going to just spend a little bit of time going through this. But essentially the process that we used is we took the WoFS ensemble and did a 1 hour spin up. And this was just to generate spread. So we kind of let all the members go off on their own, get a little bit of spread. And after that, we did the data assimilation cycling. So every 15 minutes for an hour and a half, we assimilated the simulated observations into the ensemble. And then after an hour and a half of that is the free forecast. The 18 ensemble members just run freely for 4.5 hours. And that can kind of provide insight into what the assimilation was able to do in terms of the forecast. This simulation was done with the ensemble adjustment Kalman filter using the data assimilation research testbed, or DART. And the localization radius of the observations was 65 kilometers. And we thinned the vertical spacing of the observations to every 500 meters. And I'm not going to spend a lot of time going into why we did this, but essentially it has to do with vertical correlations. If we know what the state of the atmosphere is in one point vertically, correlations give us pretty confident idea of what's going on throughout a lot of the rest of the profile. So that's why we only used every 500 meters of observations. So now I'm just going to go over the experiment terminology. Sorry for all the text on here, but I wanted to make it clear what the different experiments are and what observations they involve. The baseline experiment, what we're comparing all of the other experiments to understand the utility of the profiling observations, is the baseline, the surface rad experiment is what it's called. And the name indicates what is assimilated into this baseline run. It's surface observations and radar observations. All other experiments also assimilate surface and radar observations. So all other experiments, the title of them also starts with surface rad. This is to kind of isolate what's the boundary layer observations, the utility that they provide on top of some things that we already have, like surface observations, radar observations. So the upper limit experiment was created to just kind of get an idea of if we have this super comprehensive, super dense network that is pretty much unrealistic because of money and resources, but could possibly be realistic. It's just kind of the upper limit of what it could provide. That way we kind of know, even if we spend hundreds of millions of dollars on a network, will we even get improvements to forecast? So that experiment is the surface rad all LAM experiment. So what that stands for, surface rad, is the same thing as before, surface and radar observations. All stands for all mesonet sites. So all of the gray dots that was in the domain figure on the previous slide. And then LAM is the instruments that the simulated observations are coming from. The L stands for LIDAR. The A stands for ARI, the atmospheric emitted radiance interferometer. And the M stands for the microwave radiometer, MWR. So the surface rad all LAM experiment has a LiDAR for kinematic observations and an ARRI and an MWR for thermodynamic observations at every single mesonet site, which, as you can imagine, would be extremely expensive and not very feasible, but could kind of give us an idea of the upper limit of what a network could provide. From this, we gradually decrease the amount of sites and the amount of instruments per site to see how the improvements that we saw in the surface rad all LAM experiment deteriorate as we decrease those things, to see kind of where we could go down to without completely losing all improvements to the forecast. So that's just the terminology of the experiments and explains what they are for reference. So this is just kind of some eye candy here. This is the ensemble mean 0 to 2 kilometer updraft velocity, which is something that we commonly use to kind of diagnose where and how strong tornadoes could be. So the top is the February case, the bottom is the April case. The left is the surface rad experiment. So this is the baseline with no profiling observations assimilated, just surface and radar. The center is the surface rad all LAM, so the kind of upper limit network. And then this is the difference between the two. And we can see on here, we have the actual tornado paths plotted just kind of for reference, but more importantly, we have these black contours. And these black contours indicate where the kind of strongest updraft velocity tracks are in the nature run. So essentially, these contours serve as a proxy for where did the strongest updraft velocity actually occur. And as we can see here, the values are a lot higher within this contour for the surface rad all LAM experiment. And they're also more correctly located, especially for this experiment. Of course, there is a little bit of an increase in updraft velocity, but more importantly, the bullseye of it shifts further north, more centered with not only the nature run contour, but also it just so happens to be almost perfectly located with the observed path of the most significant tornado of the event. So already we're seeing some very interesting improvements here. But this is just from ensemble mean. And we're kind of comparing grid point by grid point. And with this type of field, updraft velocity, and with the ensemble nature of the experiments, it's not very fair to just compare grid point by grid point. So to address this, we're going to use what's called neighborhood ensemble probability. And I'm going to kind of show why that's important. So let's say this is an updraft velocity track from the nature run. So this is what we want to see. And let's say this is what an experiment showed. When you look at these, that looks really good. You would say that the experiment performed really well. And a forecaster looking at this would not have changed their forecast for this difference. It looks pretty much the same. But if you look closely, the track has just shifted ever so slightly. So if we zoom in, we can kind of see that better. If you look grid by grid, even though the overall picture shows these tracks pretty closely located, if you look grid by grid, none of the grid points, except for these couple random here, overlap between the two tracks, between the two experiments. So if you were to do like a quantitative performance analysis of this on a grid point by grid point basis, it's going to be very poor, even though from a practical standpoint, from how it would be used by a forecaster, it performed really well. So to address this, we use what's called neighborhood ensemble probability. So what we do here is assign for every grid point for all ensemble members a binary value of 1 for where a certain threshold is reached. And the thresholds we specifically assess, I'll discuss a little bit later. And then a 0 for where the threshold is not reached. So in this case, if these are the tracks, the brown grid points are assigned a binary value of 1, and the empty grid points 0. And this is done for all grid points for all 18 ensemble members. So then you choose a neighborhood size, and this could be kind of subjective. For these experiments, we use 9 kilometers. So what you do is you sum the binary values of all the grid points within every neighborhood. So within every 9-kilometer neighborhood surrounding each grid point. And you divide it by the total amount of grid points in that neighborhood. And then you sum that across all ensemble members. And that gives you the neighborhood ensemble probability. So across kind of a cushion of space to allow for a little bit of spatial differences, and across all ensemble members, so we're accounting for all possibilities, we get a probabilistic output instead of a discrete value output. And this kind of provides more information from the full ensemble sense and is more intuitive for assessing performance. So that leads to this figure, which there's a lot here, so I'm going to try to explain it as good as I can. So as in the deterministic output, the contours are, the black contours are where the nature run indicates updraft helicity reached the threshold values. And the threshold values are, for the top row, the 90th percentile of the entire nature run domain. The middle row, the 95th percentile, and the bottom row, the 99th percentile. So these 3 percentiles were focused on to kind of isolate where only the most intense rotating updrafts are occurring, so where the most extreme updraft helicity values are. The shading is the neighborhood ensemble probability, as we just discussed. For the left column, that shading is for the baselines, the surface rat experiment, the one with no profiling observations assimilated. The middle is for the big network with all of the sites and all of the instruments. And you can see right off the neighborhood ensemble probability of these various percentiles is quite a bit higher for the surface rat all LAM experiment within the contour areas where we'd expect them to be. And interestingly, the biggest improvement, so the biggest increase in neighborhood ensemble probability where we would want it to occur, is at the 99th percentile of updraft helicity. And that's right here. Up to 50% increase in neighborhood ensemble probability of updraft helicity exceeding the 99th percentile. And that's the improvement from, or the improvement of the surface rat all LAM experiment over the surface rat experiment. So in essence, it's 50% more likely to identify the 99th percentile updraft helicity values, which from a practical standpoint, it kind of indicates that assimilating the profiling observations may allow for easier identification of the most intense rotating updrafts and the tracks that they take, and therefore, theoretically, should improve the forecast performance in terms of forecasting tornadoes. So this is for the February 26th event. And this is the same thing for the April 19th event. The overall neighborhood ensemble probabilities are lower in this experiment because there was more spread in the ensembles. Because this case was so weakly forced and there were a lot of ensemble members that didn't show any convection, the neighborhood ensemble probabilities are intrinsically lower. So that's just something to keep in mind. But you can still see the assimilation experiment has higher neighborhood ensemble probabilities at all of these percentile values where we'd expect them to be. And importantly, too, is once again the northward shift in the bullseye. Here in the baseline experiment, the highest values are kind of half inside, half outside where they should be, where in the assimilation experiment, it's corrected northward and fully in the contour where it should be according to the nature run. So once again, some good results there. So to kind of quantify this performance numerically, I used kind of proxies or alternative forms of some pretty classic performance metrics, which is probability of detection, POD, and false alarm ratio. And these metrics I define a little bit differently than they traditionally are defined. And I define it by POD, so probability of detection, is the sum of the neighborhood ensemble probability of all grid points within the contours divided by the amount of grid points. So essentially it's the average in the contour, the average neighborhood ensemble probability. And the false alarm ratio is calculated the opposite way. So it's the average, essentially, neighborhood ensemble probability outside of the contours. So where we don't want values, where we don't want the tracks to be detected, what is the chance that they are? So that's the false alarm ratio. So this is just illustrating the POD. So it's shading all grid points in the contours, and that's what is averaged across. So all the NEP of all these grid points is averaged. FAR, NEP of all these grid points are averaged. So with that, we assess these metrics using a performance diagram. So performance diagrams plot the probability of detection with respect to the success ratio, which is 1 minus the false alarm ratio. So the higher you go on the x-axis, the lower the false alarm rate. And the higher you go on the y-axis, the higher the probability of detection. So a perfect forecast you would see up here on the performance diagram. This would involve 100% NEP in all of the grid points within the contours. So it's perfectly, all ensemble members are saying, yes, there will be these values here, and 0% everywhere outside. So there won't be elsewhere. That's a perfect forecast. The worst possible forecast we'll see down here on the performance diagram, it would be 100% for everywhere outside the contours and 0% for inside the contours. So that's just for reference. So essentially, the further towards the upper right-hand corner you go on the performance diagram, the better the performance. And that is quantified by what's called this critical success index, which is the shading here. So this is performance diagrams for the February case. So each point, so the red is the surface rad all LAM experiment, and the black line is the baseline surface rad experiment. And each point is a percentile. So these first 3 percentiles are the ones that we had in the plots, which is the 99th percentile, 95th percentile, and 90th percentile. And all the subsequent points are every 5th percentile going down all the way to the 50th percentile. And these percentile values, remember, are of the nature run, the whole domain of the nature run. So what we can see here is the performance at the high percentiles, especially the 99th percentile, but also the 95th percentile is substantially better for the surface rad all LAM experiment. Most specifically, the probability of detection. For the surface rad experiment, at the 99th percentile, we have probability of detection of under 20%, while for the experiment where the observations are assimilated, it's over 60%. So it's a major improvement. And that the interesting thing, though, is that improvement decreases quite rapidly at decreasing percentiles. So when you're looking at not the most intense UH values, there's less improvement, although that is still there. And a similar story is told. This was for 2 to 5 kilometer updraft velocity. Everything up till now has been 0 to 2 kilometer, just to kind of get insight into another layer. And we see a fairly similar result. The improvement may not be quite as substantial at the higher percentiles, but it's more enduring. So it takes less, or it's at lower percentiles where that improvement starts to diminish more. So that's pretty interesting results. So with these diagrams in mind, and these were used to kind of quantify that like 9-panel plot in a kind of quick way. It's especially useful for assessing a lot of different experiments, which is what we do here. So the left is where we start to reduce the number of sites in the network. So once again, black is the baseline surface rad, red is the most comprehensive network, and all of these other plots are decreasing number of sites. So we have 48 sites in the green, 24 sites in the blue, and then 12 sites and 6 sites. And one important thing to note is there's pretty much no difference throughout, or very minimal difference, between the 6-site experiment and the 24-site experiment. So by quadrupling the number of sites that you're assimilating from, you're seeing barely any improvement in forecast. So that's an important result. When we're looking at more realistic networks with a realistic amount of sites, the minimum amount is probably the best for a budget standpoint, because you're getting the same improvement to the forecast that you would out of somewhere in the middle. But it is important to note that they still do not perform as well as the full 100+ site network that would come from having observations at all mesonet sites. So that is kind of an unfortunate result, but something to keep in mind. But the good part of it is that we're still, even with only 6 sites, definitely seeing some improvement from the baseline, suggesting that even kind of the most or the least lowest resolution network will still provide some improvements. So that's important. Now to the right, we are changing what instruments are being assimilated from every site. So all of these are just still the full networks, but we're removing instruments. So the red is the original. The green and blue, which you can only see one of them because they're on top of each other, is removing the green is removing, the MWR, so one of the 2 thermodynamic profilers, and the blue is removing the ARI. And what you notice, they perform exactly the same no matter what. So this instantly indicates that having 2 different thermodynamic profilers is certainly not necessary, at least for this particular case. But what's interesting is these experiments, aside from the 99th percentile, perform almost exactly the same as the full, which indicates that having either thermodynamic profiler might not have that much of an impact. And that is reiterated by the brown plot here. This is where the LiDAR is removed, but both thermodynamic profilers are kept. And this barely improves from the baseline surface rad. So when you take the LiDAR out, almost all the improvement goes away, which indicates that the kinematic observations provided by the profiling network are having a lot more of an influence on the performance of the forecast than the thermodynamic observations. An important thing to consider, though, with that is the nature of this event. Remember, it was this extremely strong flow regime. So changes in thermodynamics locally are going to be pretty much entirely dominated by advection. So we can easily derive thermodynamics theoretically from the kinematic field, just because all thermodynamic changes are probably mostly a result of advection. So that's an important thing to keep in mind. Further experiments with cases where it's a relatively quiescent environment, I hypothesize, would be a little bit different. The thermodynamic observations might be more helpful for these because changes in thermodynamic state variables might be more related to things like radiation and evapotranspiration and more localized processes that kinematic observations aren't going to provide insight into. So a good result, but it could be isolated to this case. That's something to keep in mind for future work. Now we'll look at the April case. And we see relatively similar story, but the improvement provided is definitely lower. And that's partially due to the fact that the neighborhood ensemble probabilities are intrinsically lower already due to the increased ensemble spread. But there is still some improvement evident at the higher percentiles. An important thing to look at looking at these performance diagrams is to focus more on the points and less on the lines. So for example, looking at the 95th percentiles for the surface random experiment, it's quite a bit still further towards the good performance area than the surface rad. That's actually dominated, interestingly, by improvements to the success ratio, so decreasing chances of false alarms. But there is still definitely improvement in the probability of detection. And that's still evident at the 90th percentile and 85th percentile. But interestingly, when you go below that, the performance of the surface rad LLAM experiment actually goes below the baseline, which is a really interesting result that I think probably has something to do with the fact regarding the limitations of OSSEs, the intrinsic limitations of OSSEs, in the fact that the nature run is still a model. It might be the best performing model, but it's still not realistic. So kind of a major speculation, this might be completely wrong, that could be coming from this is that assimilating the profiling observations are allowing for the model to go more towards a realistic case and maybe away from the environment represented by the model nature run, which is why the performance is actually worse when you're comparing it to another model. So that's just kind of a speculation. Here is the same thing we saw for the other case, but for the April case. So decreasing the amount of sites and decreasing the instruments. And here there is kind of less overall change for both sides. So as you decrease the number of sites, yes, you're decreasing performance a little bit, but not a ton. It's all relatively similar, which is a good result because it indicates that we might not need the super dense network with a ton of sites. While it does technically perform better, it's not, monumentally better where it'd be worth spending multiple orders of magnitude more money. And then changing the instruments, we see kind of mixed results, but interestingly, the experiment that takes out the LiDAR observations still performs the worst relative to all others. So even though this case had a less potent kinematic environment, we're still seeing that the kinematic observations provided by the LiDAR are probably contributing the most to the improvements that we're seeing to forecast performance. So some key takeaways from these experiments. First of all, the surface rad LAM experiments show us that with the kind of upper limit of what a network could be, we are seeing some pretty significant improvements in terms of the ensemble probability of detecting specifically high updraft helicity values, which conveniently is most relevant for forecasting tornadoes. Another important result here, another key takeaway, is for strong flow cases such as these, and also such as a very large percentage of severe weather environments, the kinematic observations are providing a lot more improvement than, thank God that didn't happen till now, than the thermodynamic observations. So that's an important result and something that definitely needs to be explored further. And we could do that by seeing if we see similar indication in the case of kind of a quiescent environment where the flow is not as strong and advection is not dominating localized changes in thermodynamic state variables. And then finally, while the improvement that we see to the forecast does decrease when we reduce the amount of sites that we're assimilating from, there is a point where there's a wide range of site numbers, at least from what we can, or what the experiments that we did run, where there's not a lot of change. Like we didn't see much difference between the experiment with only 6 sites and the experiment with 24 sites. So that's important, and it's going to help us to inform how to find the optimal balance between cost and utility of a potential operational boundary layer profiling network in the future. Thank you.
We can open for questions, and questions are available online. We already have one raised hand online, so I'll take that question first while we're in turbulence. So I don't know if you want to acknowledge Corey, because I don't think you can probably hear me. So if you want to ask Corey.
Hey, Corey, what's your question?
Hi, great talk.
Oh, hold on. Okay, sorry, start over.
Okay, great talk. I appreciate Aussies. I know not everyone does. Some people, I think, in my opinion, get a little hung up on, you know, the limitations that you stated, that obviously the nature run is not a perfect emulator of the atmosphere, and sometimes it could be tough to simulate the observational errors very realistically, although it sounds like you guys took some effort to do that. But I think despite those limitations, Aussies are still very valuable. So my first question, and depending on how long this takes, I might just save my second question for after everyone else has a turn. Your UH percentiles that you computed, are those computed over the whole domain, or was there some sort of condition imposed?
Yeah, that's a great question. I probably should have made that more clear, but originally I did calculate those over the whole domain, but what I found is it was kind of the zeros, the very wide area of zeros, kind of made it not as useful to do that, if that makes sense. So I actually calculated the percentiles across all greater than 0 grid points.
Okay, I guess I'd have to think about that. I mean, yeah, I'd have to think about that. I mean, obviously, it makes the interpretability of those percentiles a little harder, and I think people are used to seeing like really high UH percentiles used, like 99.95th percentile, when they're computed over the whole domain. Okay, so then, because I was wondering, for example, why you were looking at results with a 50th, you know, 50th percentile for UH, because, you know, the 50th percentile usually would be about 0, but okay, that makes more sense now. Okay, that was quick enough. If no one minds, I'll go to my second question. If you want to go back to your slide showing the experimental setup and how you generate the like the spin up and data assimilation. Yeah, right there. You may have said it, but how do you compute the initial conditions for the other 35 members other than the worst 3-kilometer member?
Sorry, can you repeat that?
So you explained that you're using the 3-kilometer, the worst 3-kilometer WoFS member to as your initial state to get this going. But you are, of course, starting off with 36 different states that you're spinning up. And so I'm wondering how those other 35 states were generated or derived.
Yeah, that's actually a really good question. I'm glad you brought that up, because it's something that I need to familiarize myself better with. Because unfortunately, when I started this work, this whole process had already been done. So I kind of picked up after all of this had been done. So I'm really glad you brought that up, because it's definitely something that that's a really good question. I should look into that myself.
Sure. I understand. My guess would be that the original 3-kilometer ensemble, the perturbations of each member from like the ensemble mean may have then been added on to that worst 3 kilometer member to generate the rest of the 36 member initial conditions, and Lou's giving a thumbs up, so I'm guessing that's correct.
Lou would have the answer to this question because he's the one who kind of guided us through
Okay.
experiments. So,
and Josh says that is correct. All right, thanks, guys.
Thank you, guys. And thanks for the questions, Corey.
Yep, great work.
Thank you. Yeah.
So you're using a 65-kilometer horizontal localization radius. I was wondering if you like quite experiments, you change that or possibly the adjustable base of site.
Yeah, that's a really good question. That unfortunately is kind of another thing that was decided upon before I kind of started working on this project. But we did explore it briefly. And from what I understand, this localization radius just kind of seemed to be the most useful for kind of interpreting the experiments, if that makes sense. But yeah, and another reason why that was actually something that originally I was going to mess around with a lot more and have that be kind of a bigger focus. But there's so many different variables that could be changed with these. That was one thing that I decided to not really explore as much because it has more to do with the DA process and which is still important, but not quite as much to do with the network itself, which is kind of what I wanted to primarily focus on. But I think that's something that would be extremely valuable to look further into in the future for sure.
So sort of related questions to that as well. So for the two cases, were in the case of one or the other, were there like mesoscale boundaries?
That's a really good question. If we go back to kind of the reanalyses, with the February case, we of course had a ripping cold front. And that was kind of all that we could really pick up on because it was very much dominating the forcing. But for this case, of course, we have the dry line, but this is a type of case because it's a very conditional environment where those small scale features and localized boundaries could be very important. So another part of this project that I really want to go into is actually looking for those kind of things and actually seeing how these observations can be used to identify features and the evolution of those features. So yeah, that's a fantastic question, and it's a question I have myself that I really want to look into when I have the time.
Thanks, man.
Yeah, thank you.